Okay, what if I told you that to measure time, you don't actually need a starting point? That you could just look at an event, right in the middle of it, and just know how long it's been going on? I know it sounds like something straight out of science fiction, but it's the reality of a brand new kind of clock we're going to dig into today. So how do we get our heads around this? Well, here's the plan. First, we'll talk about the clocks we all know and use every single day. Then we'll see why they totally fall apart in the bizarre world of quantum physics. After that, we're diving into the solution, which is just brilliant, a clock without a start button. We'll break down how it reads what are basically atomic fingerprints, and finally, what this all means for the future of, well, measurement itself. All right, first up, our everyday clock. You know, it's built on a beautifully simple concept we all get: the difference between what happened then and what's happening now. I mean, think about it for a second. Every stopwatch, every clock on your phone, they all work the same way. They count the ticks between a starting point and an ending point. They absolutely need a then and a now to tell you how much time has passed. But this new quantum clock, it doesn't need either one. And that right there, that is the fundamental, game-changing difference at the heart of this entire breakthrough. Okay, so let's get into the problem this wild new clock is trying to solve. This brings us to the quantum stopwatch problem. You see, when you zoom way, way down to the tiny scale of individual particles, our normal rules for telling time, they just don't apply. The whole idea of now starts to get really hazy. So this is the big puzzle physicists were stuck on. At this super tiny quantum level, what do you do when your starting line, your now, just dissolves into a fog of uncertainty? You can't use a stopwatch if you don't even know for sure when the race began. It's totally useless. And this brings us to the absolutely revolutionary solution from a team of researchers at Uppsala University in Sweden. They came up with something incredible, a way to measure time without ever needing a start. So what's the secret? Well, the key to their whole method is a very special kind of atom called a Rydberg atom. The source article described them perfectly as the overinflated balloons of the particle kingdom, and that's basically what they are. Scientists use lasers to pump them full of energy, which puffs them up by kicking an electron into a really high-energy orbit, super far from the atom's core. And this is where it gets just wild. The lead researcher, Marta Berholtz, put it perfectly. She said, "You don't have to start the clock. You just look at the interference structure and say, okay, it's been 4 nanoseconds. Just think about that. You're not counting from zero. You're just looking at the final result, and it tells you the answer. It's almost like looking at a photograph and instantly knowing exactly how long the shutter was open." Okay, so how in the world does that actually work? How do you just read these atomic fingerprints? Well, to get it, you kind of have to shift your thinking. See, classical physics, the physics of our everyday world, is predictable, it's linear, kind of like beads sliding on an abacus. But quantum physics, that's way more like a roulette table. It's a game of chance and probability. You don't try to track the ball's every bounce. You just look at what number it landed on to know the final outcome. The magic here is all in wave interference. The scientists create multiple quantum waves, which they call Rydberg wave packets, all inside that same puffed-up atom. As these waves spread out and overlap, they interfere with each other, creating a totally unique pattern. You can think of it like dropping a few pebbles into a perfectly still pond all at once. The complex ripples they create form a distinct, one-of-a-kind pattern. Well, that pattern is the fingerprint of time. So here's the play-by-play. First, they take helium atoms and puff them up with lasers into those Rydberg states. Then, they generate multiple waves inside them. They just let those waves do their thing, evolving and interfering with each other. And then, for the final step, they just read the pattern that's left behind. That unique fingerprint is the timestamp. Each possible pattern corresponds to a very specific, known amount of time. So yeah, this is some seriously cool science. But what's the point? What are the real-world implications here? That brings us to our final section. The future of measurement. Why does a clock that doesn't need a start button actually matter so much? It matters because by reading this unique signature, scientists can do something they're calling quantum timestamping. They can look at incredibly fast events happening on the quantum scale and figure out exactly how much time has passed without ever needing a clean start or a clear stop. And the precision they can achieve is just staggering. We are talking about the ability to timestamp events that last as little as 1.7 trillionths of a second. That is an absurdly small amount of time. It's a level of detail that was basically impossible to capture before without a perfect start and stop signal. And honestly, this is just the beginning. The research team is imagining they could build a whole guidebook of these time fingerprints by using different kinds of atoms or by hitting them with different laser energies. This would make the whole technique incredibly versatile and could be used to improve all sorts of other ultra-fast measurement methods in science and technology. So let's just end on this thought. We've just looked at a completely new way to measure time, one that throws our most basic idea of then and now right out the window. And it really makes you wonder, doesn't it? If we can fundamentally rethink something as basic as a clock, what other parts of reality are just out there, waiting for us to find a new way of seeing them?